So yesterday we are discussing about logistic regression. Uh, so we will continue. Uh, so this was the example. Okay. So now the y-axis in logistic regression is transformed from the probability of obesity to the log odds of obesity. So just like the y-axis in linear regression, it can go from minus infinity to plus infinity. We discussed earlier that here along x-axis you are representing the weights of mouse, and along y-axis you are representing whether the mouse is obese or not obese. Okay, dichotomously you are representing. So in this case, what you are doing, you are transforming the y-axis to the log odds of obesity. Okay, so let's see what it will happen, and also you can see that the dotted line is fit to the data to predict the probability a mouse is obese given in the weight. So how it is given? That it is given by the ratio of the odds at the, what is odd, you need to know. The odds are the ratio of something happening divided by to something not happening. This is actually known as odd. Suppose the mice that are obese divided by mice that are not obese. If you take the ratio, then that is known as the odds of obesity. And you will be taking the log of the odds of obesity. Okay, the log version you are taking. Now let's transform this y-axis from a probability of obesity scale to a log odds of obesity scale. So what you will get, p suppose is the probability of a mouse being obese. Okay, then the mouse will not be obese. The probability will be 1 minus p. Okay, so p divided by 1 minus p of log of p divided by 1 minus p, this we are taking. Okay, so now let's take a look at this. Okay, suppose when we plug, suppose p is equal to 0.5. So if you put p is equal to 0.5 in the logit formula and do the math, log 0.5 divided by 1 minus 0.5, it will become, if we plug, suppose, then we will get, this is like this. Why? Because it will come out to be 0.5 divided by 0.5 log 1. Okay, so the value of log 1 is equal to 0. So here you are plotting, you are saying we can get 0, the center of the new axis. Okay, so you are transforming, basically here you are transforming this S curve, sorry, the y-axis you are transforming into the log version, log p divided by 1 minus p. Now suppose if we plug p is equal to 0.731 into the logit function and do the math, then in the similar way you will get log 2.717, which will be equal to 1. Okay, so in this way you will be calculating, and you can see that earlier it was the scale of y-axis was from 0 to 1, but if you take the log odds of obesity, then this scale will be from minus infinity to plus infinity. Okay, because you are taking the log version, so it can be any value of p you can plot, and it can be even the infinite value you will be getting. So if we plug, suppose p is equal to 1, then 1 minus 0, the logit function, and do the math, ultimately we end up with log odds of obesity on the new y-axis. This means the original samples that were labeled obese are at positive infinity for the new y-axis. So you will get the value of positive infinity. And similarly, 0.5 to 0 on the old y-axis is traced out from 0 to negative infinity on the new y-axis. So ultimately, we end up with the log odds of obesity on the new y-axis. And the new y-axis transform the squeezed line into a straight line. So this line will be, actually, why we are doing this? We are doing this so that we can, this curvature of the S curve, like this curvature we can form into a straight line. Okay, so uh, we can draw a candidate best fitting line on the graph. The only problem is that the transformation pushes the raw data to positive and negative infinity. Okay, and this means that the residuals are also equal to positive and negative infinity. And this means we cannot use the least square to find the best fitting line. Because if your data points are lying at infinity, okay, so from infinity you need to take this distance. So that will also be infinity. So that's why what we do, we need to project the original data points onto the candidate line. This gives each sample a candidate log odds value. Okay. So what we did, we do in this case, we we transform the candidate log odds to candidate probabilities using this particular formula. We can do this thing. Okay. So if we do this and if we do little bit calculation, then we can calculate. I'm giving you some slides. I'm showing that we can calculate the likelihood of that particular mouse. Okay, but these things are actually not required for your examination. This is just the illustration of that how the things are actually done. There are, you can see that there are some formulas, so you don't also need to prove the formula. The thing that, and the likelihood, how the likelihood is being calculated, that is also illustrated here. So these things are actually not required. What, and you can also estimate the maximum likelihood. Okay, the thing that you require, so that I am saying to you, that is this particular thing. It is actually required for you. Calculating the probability, how you will calculate the probability in logistic regression. You just take a look at an example. Suppose the data set of pass or fail in an exam for 5 students is given in the table below. Okay, if we use logistic regression as the classifier and assume the model suggested by the optimizer will become the following the odds of passing a course. Okay, so you can see that our studies, this is the independent variable and this is the dependent variable result, that pass or fail. You can see 29 hours is failing, 15 hours fail, 33 pass, 28 pass, 39 pass. And this will be also provided in the question. Log odds is equal to minus 64 plus 2 into hours. Okay, this will be provided in the question, and this can also, you will calculate, if you give the data, you can calculate it from the Minitab. Okay, you will face no problem. And you are hearing here, you are actually using the sigmoid function, okay, which is given by 1 by 1 plus e to the power minus x. Now the question is how to calculate the probability of pass for the student who studied 33 hours. Okay, so how you will calculate? You can see that the probability P, it is the function, this function is given by 1 by 1 plus e to the power minus x, or here you can also put z and x, both are same in this case. So the equation is given by minus 64 plus 2 into hours. Okay. So in case of hours, you put here the 33 value, the value of 33. Okay, hour studies. So you put these values and you will be getting the value of 2. Okay. Now this value of 2 you put here. Okay. So if you put this value, then you will be getting the value of probability 0.88. So a student who studies for 33 hours has a 88% chance of passing the course. Okay. Now another question is, at least how many hours the student should study that makes sure will pass the course with the probability of more than 95%. Okay. So in this case, you 95%, it means 0.95, it is the probability. So you put here the 0.95. Okay. So you will be calculating the value of if you put here 0.95, so you will be calculating easily e to the power minus z, that you can calculate, and also uh, the if you know the value of e to the power minus z, you can obviously calculate the value of z or the x, which will be 2.94, because the p is given. So if you put the value of p, you can easily calculate the value of z or the x, and it will come out to be 2.94. So uh, at least this much hours you need, sorry, so it will be calculating, it is just the value of z is equal to 2.94. Now you need to plug in these values. Okay, you will put z is equal to 2.94, this you will put in this particular equation. So if you put this, then uh, you will be calculating the value of the hours, which will come out to be 33.5. Put here z is equal to 2.94 and the value of the hours that you will be calculating, because the log odds value you are actually calculating from here. Okay, the log odd values you are calculating from here, because 1 by 1 plus e to the power minus z, it is actually representing your x or z or the log of odds. This value is given by this. So now another case is provided, the logistic regression coefficients in the context of testing if a discrete variable like whether or not a mouse has a muted gene is related to the obesity. Finding out logistic regression coefficient with the discrete x or independent variable. So the example that we have provided here, in this case you can see that the independent variables, they are continuous in nature, but in some cases you will also find that the independent variables are also discrete in nature. So in this case, how to find out the probability, so that is also given here, the explanation is done. Okay, so I'm not going into that much details of these things, but you can if you put these values and if you select the option the logistic regression in Minitab, you can very easily find out all those coefficients. Okay, it will automatically calculate it. These kinds of equations, it will be automatically provided by the Minitab software. You don't need to do all these things. Okay, I mean, these, even if you do not know, there is no problem. So now we can see one comparison between the linear regression versus the logistic regression. So just first take a look at the definition. In case of linear regression, it is actually being used to predict a continuous dependent variable based on the values of the independent variables. In case of logistic regression, it is used to predict a categorical dependent variable based on the values of independent variables. Variable type, in case of linear regression, this is continuous dependent variable. In case of logistic regression, this is categorical dependent variable. Now, estimation type, in this case, in case of linear regression, we use a least square estimation. In case of logistic regression, we use maximum likelihood estimation. The equation is given by, in case of linear regression, it is like y is equal to b0 plus b1x plus the error terms. And in this case, logistic regression is calculated is equal to constant term plus b1 x1 plus b2 x2. In this way, it is calculated. Best fitted line here, this is the straight line, and in case of logistic regression, you know that the curve, the sigmoid curve is there. The relationship between dependent variable and the independent variable, in case of linear regression, the linear relationship between the dependent and the independent variable, and but in case of logistic regression, linear relationship is not mandatory. The output, in case of linear regression, predicted integer value, but in case of logistic regression, output is predicted binary value 0 or 1. But in actually it may not be 0 or 1, but we treat it like 0 or 1. Suppose I have told you earlier that if the probability is 40%, suppose we will assume that the mouse will not be obese. But if it is 60%, then we will assume that the probability of this mouse will be obese. Okay. And the output, the applications, the business domain in forecasting sales, this is quite, it is huge. It is widely used. Okay, linear regression is widely used actually. And in case of logistic regression, it is basically used for classification based problems, cyber security, and also in case of image processing. Okay. Uh, so now we will move into the part of hypothesis testing. But before discussing the detailed about the hypothesis testing, some very important concepts or the definitions we should know. Okay. So first, take a look at uh, the definition of the confidence. So a confidence interval is a range of values we are fairly sure our true value lies in. It is represented by CI, confidence interval. Okay. Let's take a look at an example. Suppose we measure the heights of 40 randomly chosen men and get a mean height of 175 centimeter. Okay. And we also know, suppose the standard deviation of mean's height is 20 centimeter. So what will be the 90%, 95% confidence? How you will the 95% confidence interval for this mean? Okay. So you have already got the mean of 175 centimeter. Okay. So you put it plus minus 6.2 centimeter, which is actually the sample error. Okay. So how you will calculate the sample error? The sample error is calculated by Z into S divided by root N. Okay. Z is the chosen Z value from the table. S is the sample standard deviation divided by root n. N is the number of observations. So in this case, you can see that the 40 observations we have selected. So here we put the 40. Okay. And in case of ACE, standard deviation, it is, you can see that it is uh, 20 centimeter. So you put here 20. So 20 divided by root under 40. You put these values and Z value. What will be the Z value? Z value will be 1.96, because for 95% confidence interval, the value of Z will be 1.96. Okay. So you put here these values, you will be calculating the sample error. So if you do plus and minus, then you will get the range. If you do 175 plus 6.2, then it will come out to be 181.2. And if you subtract 6.2 from 175, then you will be getting 168.8, this value. The this is the this is another value of the range, another side of the range. Okay. So these range from 168.8 to 181.2. This is actually known as the confidence interval for this mean of 175 centimeter having a standard deviation of 20 centimeter. Okay. The probability that the mean from any given sample will fall within 1.96 in both sides from the true mean is 0.95 or 95%. This means that if we repeatedly compute the mean from a sample and create an interval ranging minus 1.96 to plus 1.96, this interval will contain the population mean 95% of the time. Okay. So what it is explaining? It is explaining, suppose if you have a look at this example, confidence interval. So this says the true mean of all men is likely to be between 168.7 centimeter and 181.2 centimeter. Okay, what is meant by true mean? True mean means actually you are here. True mean means the population means, because you have just taken the sample of 40 randomly chosen men. You have no idea about the population because you have not taken the data for each and every man. So it is expected that the true mean or the population mean will lie in between the 168.8 to 181.2. But it might not be. It is expected, but it may not be. Why? Because the 95% says that 95% of experiments like we just did will include the true mean, but 5% won't. So understand the way experiment has been conducted. If we conduct such kind of test, and if we again select suppose 40 randomly chosen, if we take 40 randomly the data from 40 randomly chosen men, then again some other value of mean you will get. Okay. And some other kind of standard deviation you will be getting. Okay. So that you may not get uh, that particular the range may not include the true population mean. Okay. So what does it mean? It means in case of the 95%, it means the probability that the mean from any given sample will fall within 1.96 in both sides from the true mean. Consider the true mean, I mean the population mean is 0.95 or 95%. This means that if we repeatedly compute the mean from a sample and create an interval ranging from minus 1.96 to plus 1.96, this interval will contain the population mean 95% of the time. But in 5% case, it will not uh, be, it will not lie within the uh, within this particular with the true. So uh, this is so now take a look at what is this is the thing of the concept of confidence interval. Now one thing you can ask that how these values are actually calculated for 80% 1.28, 85% 1.44, for 90% for 95% 1.96, how these values are calculated. Actually, earlier I told you different types of distributions. Okay, right? You can see the normal distribution here. Yes, yes. I'm copying this and I'm going to paste it here. Yes. So here you can see that this is the normal distribution, and here the probability density is given. Okay. So in case of when you are using this normal distribution, or in case of standard normal distribution or Z distribution, what will happen? You the mean will be 0. That means mu will be 0, and the sigma or the standard deviation will be 1. Okay. So from plus 1.96 to minus 1.96 in this particular range, if you integrate this function, you will be getting the value of 0.95. Okay. If you suppose from 1.28 plus 1.28 to minus 1.28, if you integrate the function, you will be getting the value of uh, no, you will be getting the value of 80, 0.8. So the 80% will be that. So in this way, we can actually calculate this particular table. Okay. So, now take a look at the definition of confidence level. So in case a confidence level is a range of values that is likely to contain an unknown population parameter. If you draw a random sample many times, a certain percentage of the confidence intervals will contain the population mean. So this percentage is the confidence level. So for example, if we select 100 samples of same size, it is expected or likely that if this is your 95 of the confidence interval obtained from them will contain the true mean or the population mean. So these 95 will be termed here as the confidence level. Okay. And how can you calculate the significance level? You can calculate the significance level alpha is will be given by 1 minus confidence level. In many cases, you will see that the alpha value is considered as 0.05, because when you consider the confidence level as the 95%, okay, or 0.95, you take the value, so automatically your the significance level, it becomes 0.05. Okay, so so now we will a look at the of the hypothesis testing. Okay, so uh, so in case of in our daily life, significance is actually meant as big improvement. Okay, but the statistical significance indicates that we have evidence that the result we see in the sample also exists in the population, and statistical hypothesis testing is used to determine whether the result of a data set is statistically significant, or is the difference in the evidence the public. Okay, this I have already told you that in case of hypothesis testing, the main objective of the hypothesis testing is that the kind you don't have the idea about the population, because you can only do while conducting survey, you will only take the data from the samples, you have no idea about the population. Okay, so hypothesis testing provides you the idea of the population at a particular confidence, or at a given that whether that kind of observation that you are having, suppose you have got some three mean value we have got for three different methods, so whether that is the reflection for the population as well, so that you can check through the method of hypothesis testing, that the kind of results that you are observing in case of sample, whether it is also true population, or it is just because of the random sampling process. Okay, so that you can observe. So a test that is conducted to show whether the mean of the sample is significantly greater than and significantly less than the mean of a population is considered this two-tail test. So you here we are discussing about the two-tail test and one-tail test. Okay, so let's take a look at the definition. A test that show whether the mean of the sample is significantly greater than and significantly less than the mean of a population is considered a two-tailed test. And a one-tailed test is a statistical hypothesis test set up to show that the sample mean would be higher or lower than the population mean, but not both. Okay, so in this case we use, so when you are basically interested to show that higher, greater or lower in that better and also lower both side you want to test, then you use basically a two-tail test. But in case of an one-tail test, you want to test whether it is higher or lower. Okay, so just like this. Okay, so we will see in the example later on, when we will discuss some about the some examples. We will give you the examples of a two-tailed test, and we will also give you some examples the one-tailed test. And this is actually very easy to understand. You will see. And hypothesis testing, it will always provide you a test statistic. A test statistic is a random variable that is calculated from sample data and used in a hypothesis test. Formula of test statistic will vary based on the type of test statistic, or sorry, based on the type of test. There are test statistics based on different, it will be test. There are different types of test statistics based on different types of tests like Z test, T test, F test, chi-square test, etc. So we should conduct tests depending upon the problem statement. Alternatively, you can also use the p-values representing the probability that random chance could explain the result. So there is you can uh, how can you take the you can test you can take the decision of the hypothesis testing either from the test statistic, the value of the test statistic, or also you can take the decision based on the p values, and they are corresponding to each other. That means the p value is calculated only based on the test statistic. And there are two hypotheses. One is null hypothesis, which is represented by H null or zero, and also research hypothesis. Okay, HA or H1. Why this is termed as research hypothesis? Because in any research, okay, whenever you propose something, you are basically proposing the research hypothesis or the alternative hypothesis. It is not something called the null hypothesis as such. Okay, and the null hypothesis and alternative hypothesis are analyzed by determining the test statistic and p value. In the modern era, test statistics and p values can be easily computed by you just compare your test statistic with the cutoff statistics as found in particular table depending on the type of test, and obtain p values with the given p value in the problem. Okay, mainly we basically we in this particular case the test statistic, it is using it from, I mean, using the value of the test statistic, it is little bit difficult. Because why it is difficult? Because you need to go through the chart. Okay, you need to find out the cutoff value, compare whether your cutoff value is greater than or less than the test statistic that you need to find out. Okay, but in this particular case p value, it is very easily you can understand, because usually these tests are carried out by taking into account, you know, alpha at alpha is equal to 0.05 level, you conduct those tests. Okay, so if your p value is less than 0.05, you come into the conclusion that your null hypothesis, you can reject your null hypothesis. Okay, but if your value is greater than the 0.05, then the conclusion is that you do not reject your null hypothesis. That means there is not enough evidence, whatever you are proposing in the research hypothesis or alternative hypothesis, there is not enough evidence. Okay, that your the population mean it has also changed. Okay, so we will another class we will discuss more about the p values and what is p value and what are the null hypothesis, I mean how to conduct all those things. We will give you a practical example, and this practical example we will discuss. I am going to end this class now. I'm going to stop the recording.